Hi, this video illustrates the data path for the following instruction: add S1 T3 S5. When it's executed on a MIPS single cycle CPU. Here is the single cycle architecture of MIPS. I'm going to show you all the details of the data path when we are running the following instruction in MIPS. The assumption is the PC value currently is at 0x1000, and this is the current instruction. For the sake of simplicity, I have written the opcode for this instruction, which is 0, the RS, which was T3, which is going to be at index 11 of the register file. RT, or the second source register, S5, which is at index 25 of the register file, and RD, which is S1, that's the destination register, and S1 is stored at the index 17 of the register file in MIPS. The shift amount is 0 and the func value is 32 for add. If it was a sub, then the func was 34. For different R format instructions, the func is different. For example, and it's going to be 4, so on and so forth. So let's begin by annotating all the wires in this architecture, in this picture, and specifying the data path by highlighting those wires that are active in this instruction. So I'm going to begin writing down the values of different wires. The current PC, as I said, it's going to be 1000 or 1000. That's the value that is given to the read address of the instruction memory. The instruction memory is responsible for fetching the write instruction. So the write instruction is going to be fetched here on this line, and then this line will be forked. You have different pieces of the line in this shape, in these wires, as you see on the top one, which is 31 to 26. We do have the opcode, which is full zeros. You have like 6 bits of 0. This one is 6-bit long, so I can represent it this way. I say this is 6-bit long, and the value is full zeros, 0, because the opcode was 0. Remember, this 0 is going to be given to the controller of the whole CPU, and the CPU controller is going to set these orange wires, which I call them the control wires, or the control signals of the CPU, with proper values. I'll tell you the value of each one of them. And also the other wires, like this one, the instruction 25 to 21 will get the value of the first source register, or RS, which was 11. I use decimal values here because it's very convenient. The second source register, which is RT, is 21, so I place 21 here. The destination register, or RD, is 17, so I will put 17 here. As you see, the 17 and 21 are going to be passed to this multiplexer. This multiplexer is responsible to pick one of the two. For R format, always the bottom one will be the picked one, because the reg destination control signal is going to be set to 1 for all the R format instructions, including the add instruction. So this is going to be 1, and because it's 1, we're going to pick the RD, which was 17, as the write register. So RD, or 17, comes here. This register specifies the register that's going to be written over this result of adding T3 and S5, right? So far we have fetched the instruction and decoded it, right, using the instruction memory, we have fetched the instruction. Using these wires, we have decoded the instruction. Now we are going to pass these decoded values or the MIPS fields to the register file. The register file is going to receive 11, which represents register T3, and 21, which represents register S5, and it's going to fetch the data stored in T3 and S5. The data stored in T3 is going to be placed here. I'm going to assume that T3's value is equal to 15, and S5's value is equal to 25, let's say. Okay, so this will give me 15, and the second read data is going to give me 25. So these are the values that come out of the output ports, read data 1 and read data 2 of my register file. Now, these two are going to be given to my ALU, where I can add the two values. 15 is going to be given directly, but 25 is going to be given through this multiplexer. This multiplexer may choose between the read data 2 and the output of the sign extender. The sign extender output is only relevant if you want to do any I format instruction, like add immediate, okay, or for example load word or store word. But for I format instruction, we're not going to pick this output. We're going to pick the other one, which is coming out of ALU, which is selected by ALU source. So ALU source, which is going to be controlled by the controller, is going to be set to 0 when you have an R format instruction. In this case, we have add, so ALU source is going to be 0, right? And the read data 2 is going to be 25. That's going to be given to my multiplexer's output. Now 25 and 15 are going to be given to the ALU. The ALU is going to do the add operation. How ALU knows what operation to execute? These wires, this orange wire, as you see, this thick one, which is made of 3 bits, will be set by the ALU control to 0, 1, 0. In this case, I use the base 2 representation just to emphasize that this is 3 bits. How does ALU control knows what value should be passed to the ALU? The opcode that comes out of the controller will be set to 1, 0. This one has, again, 2 bits. I use binary representation of the number 2 to represent, to emphasize that ALU up is 2 bits. This 2 bits of ALU up is going to be given to the ALU control, and ALU control passes 0, 1, 0. This is a code that tells the ALU to do the add operation. For different operation, for subtract, for AND, for OR, for XOR, we have different codes, which is given to you in the assignment or in the textbook as well, so you can check this out. Anyways, so that code 010 tells the ALU to do the add operation, and ALU is going to add 15 and 25. If that everything goes well, which is going to go well, the output will be 40, because 15 plus 25 is 40, and this 40 is not going to be given to the address of the data memory. It can be given, but the data memory has nothing to do in this instruction. This instruction is an add instruction. Data memory is only active when you want to do a load or a store. For add or any other R format instruction, the data memory is useless. It's not going to be used. Therefore, the two control signals, memWrite and memRead, which are going to control the functionality of the data memory, are both set to 0. This 0 basically emphasizes that data memory is turned off for this particular instruction add, right? Anyways, this 40 is going to be go through this wire, and it's going to be given to this multiplexer. This multiplexer is going to choose the bottom wire because the mem to reg control signal is set to 0 for any R format instruction. If it was a load or a store word, the story was different. Actually, for a store word, it's not a big deal. For load word, it's going to be set to 1. The mem to reg has to be set to 1 when it's a load word, right? For a store word, we are not going to write back the data, so this multiplexer would be relevant to the selector, would be don't care. Anyways, the read the mem to reg is going to be set to 0, so we're going to grab the value 40, which comes here to pass it to the output of the multiplexer. So 40 is set to is placed on this wire. The 40, which is the result of the sum, is going to come here. This is still the value 40. It comes to this vertical line, and it's going to be given to the right data. So the right data is equal to 40, and we're going to write 40 into the register 17, which is going to be S1. So after this instruction is completed, S1 will be equal to 40, right? Which is exactly what add is supposed to do, right? So that's 40, and this is the register number 17, which is S1. Now, in order for register file to write data into the write register, we need to have the reg write control signal, which is this one, set to 1. That's going to be always set to 1 when you have an R format instruction. Because added is an R format instruction, definitely that's going to be set to 1. And that's pretty much it. The branch signal is going to be set to 0, and because it's 0, this PC SRC is 0. This PC, which was set to 0x 1000, is going to be added by 4. The result will be 0x 1004, and this is going to be given to this multiplexer. This multiplexer is going to pick this because, you know, PC source is the end of branch, which is 0, and the output of ALU, which is not relevant in this case. This is only relevant when you have a branch operation and you want to compare two registers. The 0 bit would be set to 1 if the two input parameters of the ALU are equal. Otherwise, it's going to be set to 0. But that's only for branch equal. We don't want to talk about that. This is an add operation, not a branch equal. So we're going to skip that. The branch control signal is going to be set to 0 for any non-branch operations. This is an add, not a branch, so that's why this is 0. This is 0, and anything would be 0, so PC source is 0, so we're going to pick the multiplexer's index input 0. This multiplexer output will be the same as PC plus 4, which is equal to 0x 1004. And that's pretty much it. That's when you have the next PC equal to 0x 1004, and that's going to be the next address. That means after this instruction, we're going to execute the next immediate instruction, right? Because it's not a jump or a branch, right? Now, the last thing I want to do in this short video is to highlight with different colors all the active lines. One line that was active, and it's called the critical path because it's the longest active line, is coming out of PC, gets into the instruction memory. As you see, it goes to the wire that you see here, and it gets into this line to basically find out the value of RS. Then it goes to this line to find the value of RT. Then it goes to the register file, and then it's going to get out of the register file after reading the RS and RT. Then it gets to this multiplexer, and then into this ALU, as you see, and then the result is going to be passed here downward into this multiplexer, and then this multiplexer is going to move data down to this wire. This wire is going to be passed to the write data of the register file, and that's pretty much it. That's the longest path that we have. That one has the longest delay. We call this the critical path, right? There is another path which I'm going to use green color to show it to you. That would be the PC update path. As you see, the PC will go here. It's going to be added by 4. It's going to come here. We're not going to get into the other adder. We're just going to go straight to the multiplexer. We're going to get to the input 0 and get out of the multiplexer, and we're going to go all the way, as you see, back to the PC. Right? This loop is basically the PC update loop. That's not going to be very time consuming, so it's not going to be considered as a critical path. Critical path is very important because the delay of critical path specifies the length or the minimum length of the clock cycle, because the whole instruction has to happen in one cycle. So if this yellow data path takes, let's say, 1 nanosecond to be traversed, then I can say the clock cycle cannot be higher than 1 gigahertz. Why? Because if it's higher than 1 gigahertz, then the cycle time will be less than a nanosecond. That means you don't have enough time to traverse the whole yellow path. The yellow path is called the critical path, right? Now you may say, then what happened to this, let me use a purple one, to this path when I get out of the instruction memory, I get into this multiplexer and I get into this write register port. What happens to that? That one is a that one is not so important. That's a smaller path that is not part of the critical path, because while the electromagnetic waves are going through that yellow path, the other electromagnetic waves go to the green, to the purple path and find the location of write register. That's not part of the critical path, but you need to draw it, because if you're asked to draw or highlight the data path of the add instruction. So that's it for this video. Thank you.